Thanks. So 2 days ago, I gave a very kind of broad introduction on why people care about quantum many-body systems, although I'm not so sure whether I did a good job. But so the point of view that I want to kind of advocate in these lectures is more like so what can we learn, or what can we say about quantum many-body systems from the point of view of entanglement theory, from the point of view of quantum states? Can we characterize these states? What are the kind of mathematical properties that ground states have, and specifically what makes ground states so special? What makes them so different to random states in your Hilbert space? We gave some arguments about this, and what I would like to show today, and what I would like to work towards is that depending on the dimension in which you live, actually, there's very few of these equivalence classes. So you were talking about these equivalence classes. You have this huge Hilbert space, and then somehow there's some kind of classes, okay, that and all the kind of states, quantum states that are ground states of some Hamiltonian, are somehow connected by some adiabatic path. What an adiabatic path meant is that somehow I have some interpolation. I have some Hamiltonian path between H0 and H1, and this S runs from 0 to 1. And if the gap of that kind of Hamiltonian remains open, and of course you have to kind of think about when I take the thermodynamic limit and it's uniform and all these kind of things. Somehow if this gap remains open, then we would typically say that these two Hamiltonians kind of describe the same physics. Okay, they are in the same phase. So what I would like to kind of show today is that, like in one-dimensional, that all Hamiltonians that have a unique ground state and are gapped, they effectively belong to the same phase. So there's only one phase in one dimension. So if you and one dimension again is 1 plus 1 for the quantum field theory people. So in that sense, the gapped physics is not very interesting. It actually becomes much more interesting if you also kind of impose symmetries, namely that you say, well, actually these Hamiltonians and also the interpolating Hamiltonians that I deal with, they must have some symmetry. Then suddenly actually there becomes then you get a classification that is much more interesting. I would also like to touch up into this. But the first thing that I would like to do is introduce something that is that was introduced by that was initially kind of studied by Matthew Hastings, because somehow all the proofs, all the rigorous proofs, kind of built onto this kind of something that's called Quasiadiabatic Evolution. Okay, and this is very much related to these Lieb-Robinson bounds that we talked about. So you need these Lieb-Robinson bounds to prove things. So with this quasi-adiabatic evolution, what you will kind of be able to show is that if there is a path that is gapped between somehow H0 and H1, then somehow it implies that somehow the ground state of your state psi1, the ground state at site at time in this for this Hamiltonian H1 is actually something like time-ordered exponential from whatever 0 to 1 dt h tilde t psi 0. This is a different Hamiltonian, but somehow the whole point is that there is some kind of a quasi-local Hamiltonian. So this Hamiltonian will also be kind of local. It has some kind of super polynomial decay of interactions, but still it is kind of local. And it means that if somehow there is an adiabatic path, then this effectively means that there's a very low depth quantum circuit that connects this kind of state psi1 with the state psi0. That's the kind of... Sorry?
You intentionally didn't put an I?
No, I have to put an I. But these quantum field theory people kind of confuse me, and they always... Actually, it should be a minus I, no?
Minus I, yes.
Okay. Yeah, of course. It is a... and I would like to, so for the people kind of interested, so certainly for the quantum people in quantum information, these kind of papers of Hastings are extremely kind of appealing, because it really uses the language that we're used to, and somehow if you want to understand any of these papers, you should kind of understand this concept of quasi-adiabatic evolution. That's why I will try to kind of introduce it to you. So this is a local Hamiltonian. So what it means is that, so like, think about a one-dimensional system. Okay, this result is valid in any dimension. But so you think about a one-dimensional system. So this Hamiltonian is something that connects these two, and then somehow maybe it also couples these three kind of particles, but with much smaller weight. And it maybe also acts on how these particles, but the weight, the norm of your Hamiltonian, somehow acting on L sides decreases super polynomially in L. And this is actually enough for this H to have something like a Lieb-Robinson bond. Okay, and that's so in some sense it's not entirely clear yet how to define what phases are, but somehow certainly a property that you would like is that these Hamiltonians that would connect somehow psi1 from psi0 should kind of have a Lieb-Robinson bond. There should be some kind of notion of causality. So why is this a low-depth quantum circuit? Is because you see the time runs from 0 to 1, and the norm of this Hamiltonian is actually bound. There's no terms that kind of grow very large. So this is a low. So the norm of these kind of things is very small, and then you can principle kind of approximate this evolution, of course, by doing a Trotter expansion, just to use Trotter decomposition. The Trotter decomposition for time-ordered exponentials is actually not more difficult than for you can just use the same kind of formulas, and you see that this leads, of course, to a low-depth quantum circuit. But by low depth, I mean really kind of you can do things in parallel, okay? So you can do something here, you can do a gate here, you can do a gate here. I don't discount just for depth 1, okay? The thing is, it's low depth in the sense that there's very few, if you count somehow the number of gates that act on one qubit, this will kind of be very low depth, and you want this certainly to be kind of sublinear, the system size. Of course, like we said before, if this would kind of grow linearly in the system size, then it would probably be, or polynomially, then you would be able to kind of, this would also allow to do quantum computation, and you would probably be able to kind of prepare everything. So it's very important that the depth of this is like constant, or maybe logarithmic, or even maybe square root of n with n the size of the system, but somehow it should be low depth.
This is not only one dimension.
No, this is of course true in any dimension. Okay, so let's try to see how to proceed with this. Yeah, I'm not.
Is the existence of short-depth quantum circuits connecting ground states imply that there's an adiabatic, quasi-adiabatic?
Yes, actually, yes, that's true. That's true. Actually, because you can. So this you have a Hamiltonian here, and you can just change the sign here. And what this kind of thing will do, it will kind of broaden this thing, and indeed somehow. So I think it's actually true, but I'm not. But the implication that is relevant. So this is like the accepted definition of being in the same phase. But for all the applications, somehow what is important is that this implies this. So therefore, somehow you have to, whatever. So what we'll do is kind of. So if you can prove, for example, that there's no low depth circuit connecting these, then you're certainly sure that somehow they're not in the same phase. And I will kind of use this kind of concept to prove to you that, for example, the state in 2 dimensions, like the toric code state in 2 dimensions, cannot be in the same phase as a product state. This can be immediately kind of proven just by this concept. But first we have to prove somehow this implication. Okay, so of course I will not be kind of very rigorous in my proofs. I will just sketch you how to do this. Let me see. My notes are kind of. So what you want is what Hastings kind of did is you have this path. Okay, this is H of S, and you would like to find not just so would you like to set up some kind of Hamiltonian evolution such that this is the exact ground state along the path. So you would think, why do we care about all this? We know somehow that by adiabatic evolving somehow your state, you will kind of almost remain in the ground state, and therefore somehow this will work out. So the problem with normal adiabatic evolution is that somehow the error that you make is dependent on the norm of your Hamiltonian. Okay, but here somehow this Hamiltonian is extensive. We are kind of interested in somehow a system that becomes larger and larger and larger, and therefore the norms of these Hamiltonians kind of blow up. Okay, they kind of become all linear. So the norm of these Hamiltonian, we know that energy is an extensive quantity, so the norms of these quantities is linear, and therefore somehow if you want to make a small error to go from psi 0 to psi 1 by adiabatic evolution, the depth of the quantum circuit will have to be at least kind of polynomial in n. That's exactly, we don't want this, as argued before, because that would lead to a wrong definition. So that's why we need to do something smarter, and that's why we follow Hastings. So what he kind of came up with is some kind of a way of constructing the exact evolution. So what we are doing here is really this psi of s, this will be always, so if you start, if psi of 0 is the exact ground state of H0, then psi of 1 evolving with this Hamiltonian will be the exact ground state of H1. So there will be kind of no error whatsoever. So this is a bit, might sound strange for quantum information. We always used to use epsilons, but somehow here it makes sense to do this. Sorry? Yeah, sure. Well, yes. And s goes from 0 to 1. So you can just use perturbation theory now for this kind of thing. So you can let me quickly do that. Like you have h plus. Well, anyway, so if you do perturbation theory, first order perturbation theory, that's actually a good exercise. It's just a few lines. What you see is that actually this is equivalent. You can write this as minus the projector orthogonal to psi of s. Okay, so it has to be, because of course if you evolve psi of s, it has to remain kind of an orthonormalized state, so the evolution has to be orthogonal to your kind of state such that the norm is conserved. So this is just a projector, but this is not really important. Then you have 1 over h minus e of s, with e of s the ground state energy at time s, times somehow delta over delta s of h of s. In this particular case, this is of course just h1, but this is actually true for any path, times psi of s. Okay, so you can, this is really kind of just an exercise in first order perturbation theory. So you see what I get is just a 1 over h minus e of s times this. And now there's a kind of a trick from Fourier analysis that you can use. And this is the following. Namely, so the important thing is that this h is gapped, and you want to make use of that. Okay, so you know that the spectrum of h looks like, let's assume that the ground state energy is 0. Okay, so there's one kind of state here, then you have a gap, and then you have like typically a continuum of eigenstates. But there's no energy between 0 and the gap. Okay, there's no energy states. That's the whole assumption that this is gapped. Now in Fourier analysis, somehow there's some kind of really non-trivial results that show you that there exist functions as follows. That somehow if you take the exponential I omega t f of t, there exist such functions such that this is minus 1 over omega for omega larger than delta, and is equal to 0 for omega is equal to 0. So somehow what we want to do is basically to understand this as the Fourier transform of some function. Okay, but of course because h is gapped, we don't really care what happens with this function for values of the energy in this gap, because this h doesn't have any support there anyway. So what happens is that somehow you want to take the Fourier transform, and what is understood is that there exist such functions, f of t, that exactly have this property and decay kind of super polynomially fast. So this is this kind of thing that I talked about. There's some kind of delta times t divided by log of t. Okay, so this is basically the magnitude of this f of t is bounded above by the exponential of minus delta times the absolute value of t divided by the log of the absolute value of t. So that means that this function is decaying fast. Okay, but somehow, and so the reason why this is kind of possible is that of course there's many possible functions that have this property, because you only specify basically that function within this kind of for omega larger than the gap, or for omega equal to 0. All the rest you basically don't care, because somehow this h doesn't have any, or h minus e doesn't have any values there anyway. Okay, so and the further away delta s, somehow the sharper you will be able to make this function, and therefore the better kind of the results will be. So what you do is then just use this. So why do we need this kind of fact that this is 0 for omega is equal to 0? This is exactly kind of making sure that this projector is there, so that somehow at 0, that somehow this does not have any support on somehow the eigenstate corresponding to the ground state. This is exactly this thing. So this kind of corresponds to this. There's 1 over h minus e of s is exactly this 1 over omega. So you fill this in, and what you get is something like the integral of dt f of t e tot de IH t delta th e to the minus IH t times psi of 0. Okay, so why is this? So this e to the minus IHT times psi of 0 kind of will give rise exactly to this E of S. So you see this is, because this is an this is S. This is an eigenstate of this, so this will exactly give rise to minus I times E times T. So this E, there's a scalar, you can put it here, you get H minus E. You take the Fourier transform of e to the IHT, but we know that somehow the only values that we are interested in is this, so this gives exactly this kind of property. Okay, so now the important thing, so you see that somehow the exact Hamiltonian that we have here can be written as a sum of many, many terms. Okay, as actually as an integral, it's a continuum of terms. But the important thing is that this kind of thing is quasi-local. Okay, that the norm of some, so it happens that actually this, you will be able to bound this basically. We will be able to show that this, for kind of times that are not too large, somehow this will be very small. So what this means is that I have this kind of delta t of h. This is like, how do I change my Hamiltonian? Okay, and this, what this kind of thing does, so I have some kind of an operator that acts here. This e to the IHT will spread this out. Okay, so it will start spreading this thing out. But as we saw in the last lecture about this Lieb-Robinson bound, somehow things can only spread out at a finite speed. Okay, so at some kind of time t, this operator will have some kind of a light cone. It will kind of spread out. But outside of this light cone, this kind of thing will be completely negligible. But you see that this thing decays very fast as a function of t. Okay, so there's, because this kind of spreads, but somehow it's completely kind of, so this thing decays very fast. You see that this whole kind of terms, all these terms in this Hamiltonian are actually, will be very small. So the weight, the prefactor, the norm of these terms, for which you will have a very large support, will be exponentially suppressed. Okay, and that's the whole clue of quasi-adiabatic evolution, that there exists an exact kind of Hamiltonian evolution that gives you the exact ground state. You follow the exact ground state, and this Hamiltonian is quasi-local. The norm of all the terms in this Hamiltonian are decaying kind of superpolynomially with the distance.
I think there is something a little confusing, because the left-hand side is a function of S, and the right-hand side, the operator was S dependent.
Well, you have to put S's everywhere. But it doesn't really matter. You introduce an extra integral. So this t has nothing to do with S. Okay, so.
Should be some S left over.
Yes. Yeah, everything is, well, in the end this is, yeah. But typically, like in this part, if you interpolate like this, then of course this delta t of h is independent of S actually.
Ft minus S or something, no?
Sorry?
Ft minus S or something.
No. This t has nothing to do with S.
And the integral from
From minus infinity to plus infinity. But you see that this is kind of decaying fast anyway, so it doesn't really matter. Okay. Okay, so this means that indeed, if you have a gapped path, that automatically implies that there is kind of a quasi-local Hamiltonian that will connect this ground state with that ground state. That's what we wanted to prove, and this kind of shows it. Okay, so it's a very simple kind of calculation, but still it's very, very powerful. Okay, so let's show now by using this kind of formalism that indeed that, for example, if you have topological order in 2 dimensions, that this state must be in a different phase as states that do not have topological order. Okay, so so think about. So I guess Barbara Terhal must have kind of given a very kind of extensive discussion about error correcting codes. And at the end, somehow there's a very kind of strong relationship between error correction and topological order. So in many ways, somehow you can.
Sorry, I keep interrupting there, but I think it's in the derivative of the h in the middle of the expression. Yes.
Well, this thing is dependent on S. Oh yeah, sorry. Oh yeah, sorry. I should have. Yeah, of course. Yes. Well, as I said, somehow if you take this, then this is independent of the time or S. Yeah, whatever. Yes, but you're perfectly. Of course, you're completely right. Okay, so the thing is in a long time ago, somehow, when I was still a postdoc with John, Matthew Hastings was kind of visiting, I think, was explaining all of this, and somehow what was immediately clear when we were discussing is that that this kind of leads to a very nice way of characterizing indeed these kind of phases. This so showing that topological ordered states are really kind of in a different phase as just product states, for example. And what is topological order? You can actually define it on the level of states. So as we saw in the lectures of Verstraete, somehow what is crucial in topological ordered states is that you have kind of a degeneracy. So you have a few kind of ground states, and locally they all look the same. Okay, but this is, so if you formalize this, what this actually means is that for any local operator, local, let's say, acting on L sites, and this L can be whatever, it's much smaller typically than the system size. Okay, so for any local operator, what you want is that if you have kind of different ground states, that is O local psi j. So these are kind of, they can, of course, I can be equal to j. So these are the different kind of ground states in your topological order, that this is equal to delta ij times some function of O local. But this function is not dependent on I and j. Okay, so if you kind of paid attention to the lecture of Barbara, probably you will, this is exactly the condition for error correction. Okay, this is exactly kind of the things that come out there. So what does it mean? So it is actually very non-trivial. So it means that with local operators, you cannot distinguish in which state you are, okay, because this expectation value is independent of I and j. Okay, so take I equal to j, you don't know what kind of state you are in. But there's an extra condition here that is actually very important. That means that there should also be no local operator that allows you to map one eigenstate or one ground state to another ground state. Okay, so that's also implied by the definition. That's implied by this delta ij kind of part. Okay, so that's actually a very important property. And of course, somehow this is a bit too stringent now, because there's this delta ij, just like Adi kind of was telling. Actually, what you allow for is typically some kind of errors minus L that are exponential in the system size. So L would be kind of the system size, the number, the whatever linear dimension in your system, like on the torus. Okay, so to have a degeneracy like for typical systems, the degeneracy depends on the genus of your kind of your geometry, and somehow on a torus, somehow this L would be the linear length. And what you allow for is typically errors in the order of that are exponentially small in the system size. You all kind of, I don't want to kind of go through the example, but somehow I think all these kind of codes with a certain distance and all these kind of things, as you have seen in the lectures, satisfy this. So particularly somehow the toric code of Kitaev certainly has this property even without this kind of thing. It's really an exact thing there. But let's kind of show that indeed somehow product states do not have this property. So let's, for example, start with the state with all zeros. Okay, so let's show that there actually does not exist any other state. Okay, so that could be psi 1. There does not exist any other state somehow for which I would be able to kind of satisfy this condition. Okay, so why is this? To create somehow a state, so we want somehow a Hamiltonian. I didn't specify a Hamiltonian, but I want a Hamiltonian such that somehow would have a degenerate ground state space, and one of them is these ones. Okay, because so to be orthogonal to all these states, at least one of these bits has to be flipped, no? At least one of these zeros has to become a 1. Okay, and for example, it could be a superposition of being a 1 there, or a 1 there, or a 1 there. But you see then, if you kind of calculate this expectation value, that is not exactly exponentially small in L, it will be kind of polynomial in L. So if you kind of, if this would be, let's say, take the sum, take 0, 0, 1, and all zeros, plus a superposition of all these kind of things with 1 over square root of L. Somehow, this expectation value of a local, like you would just measure a 0 or a 1, would of course also be close to kind of 0, but somehow you would have a correction that is linear in L, not exponentially small. So you see that indeed somehow a product state, independent of what other state somehow you can imagine, cannot satisfy this condition. There is no other state, there's no companion state for this product state such that this condition would also kind of be true. Okay, so now we can go back to our kind of way of saying, well, is it now possible that there's an adiabatic path that connects somehow a Hamiltonian whose ground states exhibit this property to a Hamiltonian that has this kind of state as the ground state. Okay, so is that possible at all? Okay, so and you already kind of see that this is this cannot be true. No? So the reason is that somehow we take somehow this ground state of the toric code state or whatever state that you want. Let's call it psi 1, and by doing this kind of quasi-adiabatic evolution, okay, so this is it would be in the same phase. Being in the same phase would imply that there's a low-depth quantum circuit that connects this kind of thing to another thing. Okay, so that means that at the end, the ground state of your new Hamiltonian will be u times psi 1. Okay, so let's calculate somehow psi 1. Somehow the expectation values of this. And you can do this actually for any I and any j. What you see now is that somehow this is a low-depth quantum circuit. And this is a local operator. Okay, and exactly for the same reason as we discussed here. That means I have a local operator, and I have something that spreads it out. But somehow the time, or somehow the depth of this circuit is much, much smaller than the system size. That was the whole point. Okay, this is really sublinear. So that means that somehow this kind of thing, originally it kind of acted on this. After this, it's a bit kind of spread out. But somehow, that means that somehow you just have to change a bit the definition of your locality. Instead of L, it's L plus some other number, but that number is still much, much smaller than somehow the whole system size. So that means that independent of how you evolve somehow your state, if you stay in the same phase, that thing will still be topologically ordered. Okay, because that will just be another kind of local operator, and this property had to hold for all possible local operators. So therefore, somehow you evolve your state, well, this state still has to be topologically ordered. And therefore, it's impossible somehow to connect this state to the product state. Okay, so that immediately shows that the need for states with topological order, this kind of definitions lead you to immediately kind of imply that you can really define different equivalence classes. Okay, so it will happen that in one dimension this is not true. In one dimension everything will be connected to each other, but in two dimensions somehow you really have different kind of equivalence classes. Yes?
Somewhat of a naive question. What are psi I and psi j? Are you trying to go from psi j to psi I using a quantum circuit?
No. So this psi I and psi j's are just the ground states, the different ground states of your system. And I define topological order. A system has topological order if and only if this condition is satisfied. That's how I basically define topological order.
For any local operator?
Yes. For any local operator that is like, let's say, much smaller than the system size. But I'm a bit kind of colloquial with how precisely what do you mean how local it is. But typically it's for every I and j, but I and j are the ground states, so these are different kind of ground states. Yes.
What if I have a whole bunch of spins which are all up in the z direction, and then I stick the x operator into that?
Yeah, exactly. That's what I'm showing. But then somehow this is not true because this is like you will. So any state orthogonal to it will somehow have an error that is kind of 1 over L. The error will be polynomial, and I want an exponentially small number here in the system size. It really happens that for kind of systems with topological order, this is exponentially small. And as Adi also explained, this is the clue. This is the whole clue of topological order, that this is really exponentially suppressed. Okay, so this is.
And is f the same function for all operators, or does it change from operator to
No, it's of course it depends on the operator, but it doesn't depend on I and j. That's the important thing. Okay, so that if it would depend on I and j, by just measuring the expectation value of that local operator, you would be able to tell which ground state you're in. And of course you don't want this. But there's more here, okay? There's also that somehow this delta ij, that somehow there's no local operator that maps one ground state to another one. That's actually, yes?
This is probably silly, but I mean, I can imagine putting a topologically ordered system on like the sphere, and then it has a unique ground state still. You would imagine it's still got some notion of topological order. So how do I have this definition mapping between ground states when there's still only one?
Well, we'll have to use different tricks there. I don't know how to prove it that it's in a different phase, but of course it would be a different phase. I don't think it's possible to map it to a product state. But
so you might have to demand that this Hamiltonian, this satisfies when I'm also embedded into higher genus.
Yeah, but yeah, indeed. In some sense, it's clear. You only allow for very low depth quantum circuits, so it shouldn't matter if you're in a sphere or any genus somehow, because you don't have time anyway to kind of go around the whole thing. So.
Like you'd imagine writing the ground state degeneracy is proportional to the power to the genus.
Yeah.
In that case.
Well, I'm sure yeah, I've not, yeah, but I'm sure it's possible to also prove it for that case, that on a sphere it's also in a different phase. But yeah.
You're getting a lot of mileage out of the e to the minus L because
Yes.
I think in the example,
Yes.
in the example I just said, that's actually zero. You just have a bunch of spins, and then you consider a state that's all zeros, and then you consider it the state you get by acting on that with x.
Yes, indeed. But then the operator I would choose as x.
Oh, yeah, and then isn't it one?
Yeah, actually, then this is
No, but then the states are different. You see, so
no, but if you just flip one spin, then actually this is even violated.
yeah.
Okay, but so you would have to take you would have to do something like this. Okay, and then any local operator would actually have some support, but it would still be 1 over kind of L. Okay, because somehow locally this looks very much like the ground state, but there's kind of corrections. There's in the order of 1 over L corrections. And there's nothing else that you can do. There will always exist some local operator somewhere that will give you 1 over L.
Okay, but you're using some sort of genericity here. So that means it's not a rigorous statement.
No, well, what I wanted to prove is that, like, if you have a state of topological order that is in a different phase as a product state. Okay, and that's true for any kind of product state. That's certainly okay. So that the argument that I gave is just, yeah, well, you can certainly make it rigorous for any product state. I'm not saying that what I'm kind of sketching here is but you can really make this. But it's, I think that's the kind of intuition that is important. Yes.
What's U?
Oh, some unitary. This is U. This here. This U. It's this evolution kind of how you. This is like the time ordered exponential of that Hamiltonian here, which is a sum of many terms, but they kind of decay. They're local, physically local. Indeed, yeah.
How can you classify local operator? Does it mean local support?
Local, spatially local, really. It's not just local like in the complexity sense that it's not too, but no, it's really, it has to be kind of local in the metric that you kind of deal with.
When we talk about the scale of exponential to the minus large L, we are fixing a small L, right?
Yeah, but somehow all these kind of things should hold. Somehow you should construct families and make your system larger and larger, and somehow the scale. It's really about the scaling. How does it scale? And of course, there's a constant here, and so further. But it's really about the scaling in the system. So if you make the system larger and larger and larger, somehow this kind of property should be true. That's what I'm.
Yeah, but when we do that, we are fixing a certain small L, right? But we don't expect, like, if we allow small L to scale together with a large L, then it doesn't.
Yeah. Oh, I understand. Yeah, the small L. Well, but the small L typically, if it's half of the system size, would probably still be okay. Okay, as long as this doesn't allow you to have, like, think about something like the toric code state. As long as this operator is not something that can wind around the torus, it would be okay. Okay, so that's why somehow the support should be. Yes. No. No. So.
Very important, right?
Well, important. It really means that. Well, as you will see, actually, so indeed it kind of feels a bit counterintuitive, no? Because you have to. So, but in the case of one-dimensional systems, actually everything is connected. You will just be able to prove that everything is connected. So it just by looking at the example, you will see that it makes sense. Well, we already have a proof that it cannot be. Okay, because there are systems that are topologically ordered in 2 dimensions, and obviously they cannot be kind of connected via that kind of definition. But we have just shown that this implies this, therefore they cannot be in the same phase. Yes.
So this picture on the very beginning, so that's a space of states, right?
Yes.
So here, I guess we've just changed a little. We're now sort of talking about subspaces because it could be degenerate ground spaces, and that's why we can allow that in the
Yes.
topologically ordered case. So you, and then the product state case, you're also thinking there of some degenerate ground space of product states that has the same dimension as
Yes.
the. Okay.
Yeah, indeed. Yeah. So certainly, so if you have the degenerate ground state subspace, then of course somehow you should not kind of think about states here. You should think about the projectors on the ground state subspace.
Okay.
Okay, and that these two projectors should be connected by, but I didn't want to write it out. So I can give you another kind of very nice. So this is, I think, this is really kind of trivial, no? But nevertheless, I think it's actually pretty deep. Another kind of example to show you somehow the magic of having something like this quasi-adiabatic evolution and kind of understanding this. You can prove really amazing things. So let's prove Goldstones Theorem, okay, in 2 lines. Okay, this is of course something that Hastings did. So what we want to prove is that if, so you must have a system, so let's say you have like a lattice system in any dimension, and it should have a conserved kind of charge, okay, so it should have continuous symmetry, like a U1 symmetry. So what that means is that somehow your Hamiltonian should commute with, for example, the sum of sigma z, okay, so that's like, so there's a particle number conservation or something like that, okay, so you have a U1 kind of charge. Okay, and your Hamiltonian commutes with this. So what you can prove in 2 lines is the following, that if you have a Hamiltonian that has this property and H is gapped, then somehow the expectation value of any kind of operator that transforms non-trivially under this gauge transform, I will explain what that means. Alpha psi beta is exponentially small. Okay, so why this doesn't look like the familiar Goldstone theorem, no, but it actually is. So what you need is that these kind of operators here act transform non-trivially under somehow this kind of gauge transform. So what you need is that somehow exponential of I times sum sigma z psi exponential of minus I sum sigma z is somehow e to, I put a theta here, is somehow e to the I theta times psi. Okay, so these are kind of creation operators, or so if this is, if you would imagine that this is like the total kind of charge or spin somehow, these psi's, this should be kind of creation or annihilation operators. Okay, so they transform non-trivially under this kind of transform. And so it means that this is exponentially small. That means that there cannot be, this is basically the definition of symmetry breaking. It means that there cannot be symmetry breaking. Okay, so what it has this to do with Goldstones theorem? Goldstones theorem tells you that if you have symmetry breaking and you have kind of a conserved quantity, that means that your kind of Hamiltonian must be kind of, wait, is that the way Goldstone, I actually don't know how Goldstones theorem is typically said, but somehow if you have a gapless system, wait, what it certainly implies, if you kind of go the backwards, if you have kind of an ordered parameter, then this is only compatible with the fact that H is gapless. Okay, so you cannot have an ordered parameter without being gapless. And therefore, if you have an ordered parameter, your H must be gapless. And that's the typical Goldstone theorem.
You're thinking about, in the symmetry broken phase, the psi would get a web, not this composite operator?
Well, somehow the reason why, so this actually has to do with the discussion that we had in that. So actually, it is really the expectation value of this. But of course, these charges conserved. Okay, so think about alpha to be kind of at minus infinity and beta to be at plus infinity. Okay, and then this makes sense actually, and then you can see that this is equivalent to saying that actually there's no symmetry breaking.
So the charged operator is actually the psi, and you're
Yes.
just considering something that's U1 in there.
Exactly. So how do you prove this? It was actually a very smart idea of Hastings. So let's take our alpha here, or psi alpha here, and the beta very, very far from it. Okay, so this is, or let's call this x and y. And let's consider a sphere around x. And let's do some kind of a transformation. So instead of kind of working with h, we will kind of define h of theta is equal to the exponential of sum I as in the sphere of somehow theta sigma z times h times exponential of minus I, the same thing. So basically you do your kind of, so you only sum the terms in your charge within that kind of region, but you don't sum them outside of this region. Okay, but we know that, so again, H commutes with the whole kind of charge sector, but this sum has to run over the whole thing. But here we only kind of sum over things that are in that ball. And obviously this Hamiltonian has the same spectrum as the original Hamiltonian, okay, because it's just kind of a local unity transformation. This Hamiltonian is related to that one by just a local unity transformation. These are all local, strictly local, one-body operators, and therefore we immediately know all the eigenstates of that one too. Like we know the ground state, we know basically everything. Okay, so let's now kind of use some trick. So we have this. So this new guy. The ground state is psi of theta. Okay, depends on this kind of angle theta. And let's kind of calculate delta theta, the derivative with respect to theta of psi of theta. This kind of psi dagger x, psi y, psi of theta. You know, there's two ways in which we can do that. Okay, so either somehow we can just take the derivative of this psi of theta, but we immediately know how this, so this will kind of be done by this quasi-adiabatic evolution, okay, because we know somehow if you kind of change your Hamiltonian slowly, and somehow we know how this kind of this ground state changes, okay, because that's exactly what we did with this quasi-adiabatic evolution. But there's another way, because we of course know psi of theta exactly. This is just these local unitaries applied to this kind of region, okay, and you see that this psi, so what you have is of course that this is equal to delta theta psi u times psi x dagger. Can't put a u dagger here, a u here, psi y u dagger psi. Okay, and so let's kind of first do it in this way. So we know that this is e to the I theta psi. Okay, so immediately see, and of course you have to do it here too. So you see that this is actually nothing more than 2 times I. And then let's do it at theta equal to 0. What we get is that is equal to psi of 0 at the original kind of thing, psi x dagger, psi y, psi of 0. Okay, because this is nothing more than psi of theta. This is a local unitary. This is e to the I theta. This is a prefactor. You take the derivative with respect to an exponential, and you get just somehow your 2i times.
Only one of them effectively changes?
Well, both of them, you have to sum it, no? You change this one, you change that one. And
But you do the transformation only in a region where one of them is active.
oh yeah, sorry. Of course, I'm confused. Of course, yes. Thanks a lot. Otherwise, it wouldn't make sense. Okay, so the other way of looking at this kind of thing, however, is by saying, well, I know exactly how this psi of theta changes. Okay, this is nothing more than somehow psi, so delta over delta theta, psi of theta is this kind of Hamiltonian, this quasi-adiabatic Hamiltonian acting on psi of 0. Okay, but this, so what happens now is that this quasi-adiabatic Hamiltonian, if you kind of go through the things, it has exactly the same properties as the original one. Okay, and therefore somehow, so this thing commutes with all your terms. So this H commutes with the sum of sigma z. But you can see that actually somehow, so you have to let's see how this so this is this. So what you get here is actually somehow psi of 0, and then the commutator of this H and psi x dagger psi y, psi of 0. But now it happens that actually the only terms somehow this quasi-adiabatic evolution. So what you had was this derivative with respect to your parameter theta. But because all your terms, basically your terms commute with your Hamiltonian, this H here, this term here, only contains terms that are concentrated around that border. All the other kind of terms disappear. Of course, they are smeared out. There's also terms that act like this. There's terms that act like this. But these are kind of exponentially suppressed, as we said before. So you see immediately that indeed all these operators here are living somewhere around this circle. Psi of x is acting here. Psi of y, I don't know where it was, somewhere here. So therefore, this is exponentially small. And this is equal to this. So that means that this is exponentially small. Therefore, the order parameter is exponentially suppressed. Okay, so you have kind of a very strong version of Goldstones theorem.
Could you say again why it's exponentially small?
Okay, so your Hamiltonian. So you take the Yes. And the distance between these two operators. Yeah.
And again, why? So why is it exponentially small?
Okay, so you have your Hamiltonian kind of. So your Hamiltonian consists of many terms. Okay, it's a local Hamiltonian. And yeah, what I didn't explain exactly is also where the gap appears, no? Because this is of course crucial that H is gapped. So let me kind of. So your Hamiltonian contains somehow all these terms that act here and so further. But doing this kind of gauge transform, okay, somehow this commutes with these terms that live completely in that circle. Okay, because these are all terms that commute with particle numbers, so it doesn't matter what happens outside. All these terms commute. So the only terms that do not commute with this kind of transformation that would change are exactly the terms that go across that region. Okay, so these are the terms that go across that region. But now, of course, this is not exactly the H. It's this kind of quasi-adiabatic thing. Okay, so these kind of guys, these terms are kind of a bit spread out. As we have seen, the larger the gap is, the less they are spread out. Okay, so if you have a gap, then there will always exist somehow. You just take a distance while this kind of thing is exponentially decaying. But if it's gapless, this whole kind of thing breaks down. Okay, because then somehow this H, this quasi-adiabatic evolution is kind of completely unbounded. That's why somehow if it's gapped, then this is kind of decaying. All these terms are very small. They are just somehow the weight, and the only terms that give a non-zero contribution are the ones that overlap with this or with that other guy there somewhere. Okay, and that's how you prove it. Okay, but anyway, this was, I just tried to kind of, I wanted to show you this because that's one of these very simple examples, that extremely powerful kind of applications of this quasi-adiabatic evolution. Actually, maybe I should not have talked about it, but I think it's important that
Is the essence of the theorem that if there is no Goldstone mode, there is no other parameter?
So if H is gapped and there's a U1 symmetry, then there's no order parameter. That's what this tells.
Yeah, and if H is gapped, then there is no Goldstone mode.
Exactly.
Because Goldstone mode is
Exactly.
gapless.
So that means that if there is kind of a symmetry broke, if you break the symmetry, then it must be gapless.
Sorry.
That's
The U was the time-ordered exponential that you wrote down for the Quasiadiabatic evolution.
yes. But the thing is, it only kind of because this kind of commutes with all these terms. The only terms that are living there are kind of terms in this very large sphere. And then at the end, it doesn't matter how far these alpha and beta are. No, you can take them as far as you want, and therefore somehow it doesn't really. Yes.
So why do you need the U1 symmetry at all? I thought so if you have a gap system, at least in general that correlations are
No, connected correlation functions. This is not connected here, no? Yeah. Yes?
So this specification to this phase, this is for pure states. What happens if you increase the entropy? This regions combine, or we can define the phase as
I think for low enough energy, this actually. So I think certainly in 2 dimensions, if the moment you have finite temperature, I think all these. I think John showed this in a paper. No, there's no topological order anymore. In 4 dimensions, apparently, this would still be a different phase. Then certainly for these simple cases that we know, like the toric code state and all you add some finite temperature, then there's no topological order anymore. So that property is not satisfied anymore. But of course, this property doesn't really make sense anymore because you're not talking about states. I'm not so sure actually how, but there's certainly kind of a criterion by which you can say that there's no topological order anymore. But we are talking about degenerate ground states here, no? Because otherwise you don't have topological order. You put it on a torus, there must be somehow degenerate ground states. Otherwise, there's no topological order. Another kind of application of check how I'm doing with the time. But another application, but wait, is it already 5:30?
we started late. You can go till 6:15 and you'll be perfect.
Well, but I have only covered 1 page from my. Well, okay. So then I will be very quick. Another application of this kind of quasi-adiabatic evolution is as follows. You have.
Don't be too quick.
Yeah, but well, I have to. You have a system. So we are talking about somehow these equivalence classes, no? Which is kind of a bit colloquial, but anyway. So what we would like to, so one thing that always kind of bothered me is that we are talking about area laws. Okay, we are talking about entropy of kind of the entanglement entropy of a region, but entanglement entropy is a kind of an extremely odd thing. It's not an observable. It's not that you can make an infinitesimal change in your state. So there's something that is called Vannes inequality. It's namely you have two states, rho and sigma. Then somehow the difference in entropy can be kind of proportional to the trace distance between these two, but times the log of the dimension of the Hilbert space on which they live. So that means that the trace distance, two states can be extremely close. That means for any observable you will not see the difference. But you multiply this with somehow the log of the dimension of your Hilbert space. And if you're talking about many body systems, this of course kind of keeps on growing and kind of becomes infinity. That means that even if two states are completely indistinguishable, they can have a completely different entropy. And that kind of always bothered me about what does it mean? That means that actually that entropy cannot be a property of a state. Why do we look at entropy even? Because you can just perturb your state infinitesimally and you get a state with a completely different entropy.
Can you give a trivial example of that?
Well, you can just prove that for every rho and sigma this is true.
This is what we want, right?
I don't know, but you can saturate it indeed. Okay, and at the end, this of course has nothing to do with quantum. No? You can just assume that these are probability distributions, and this is all about the tails. So you can put lots and lots of weight in a tail that has only an epsilon kind of weight. Okay, so this would be this epsilon. You put epsilon weight, but you make the tails very different. And if you make a tail extremely long, then somehow the entropy kind of will blow up, even if the total weight of that tail is infinitesimal. And that's how you kind of get to this.
But aren't you saying the difference in the entropy is less than the trace norm of the difference of the states?
Yeah, but okay. So you can, but you can saturate. I'm showing that this is less, and indeed somehow this is what Vannes inequality is. But you can actually saturate that. There are for all kind of, you can always find examples rho and sigma that saturate this inequality. Okay, so that means that there exist states that are very close to each other but still have a completely different entropy. Okay, so what's the deal? Is that now we would like to prove that within a certain phase, in a given phase, actually this definition still makes sense. So that if somehow in a phase there's one state that obeys an area law, and all the other states would obey an area law. Originally, what we wanted to do is actually prove, go to a kind of completely general proof of area laws. So what this kind of what this shows now is that indeed, so using this Quasiadiabatic evolution is very easy, okay? Because we have this definition of Quasiadiabatic path. You take one state in the phase that supposedly obeys an area law, you assume that. Then you kind of will move that, and you can see that the number of terms, somehow there will be some kind of terms that act like this, and terms that act like this, but somehow the weight of all these terms kind of is decreasing very fast. And what we had to prove is somehow a bound on the entangling rate. Okay, so if you have a Hamiltonian acting on a bipartite system, how much entanglement can there be created by unit of time? Okay, and there were some bounds. Many people actually worked on that, like Charlie Bennett and company. But somehow their bounds were actually exponentially. They were not good enough. Somehow you have to prove that these bounds actually are good. And indeed, somehow you can prove that somehow the entangling rate is bounded by somehow something that scales like the log of the dimension of the Hilbert space on which you act non-trivially. And with this, you can indeed prove that somehow by evolving in time, somehow that the entangling rate, the rate at which entanglement increases, is bounded by something that scales like the area. And therefore, within a phase, somehow all the states obey an area law, or none of them does. So if whenever one state obeys an area law, then everything in that phase obeys an area law. And therefore, it's kind of basically enough, so at least for condensed matter kind of applications, if you want to prove an area law, you just have to prove that in every phase there's one state that obeys an area law. And again, somehow this is using this Quasiadiabatic evolution. Okay, so let me kind of talk about something completely different now. Let me back up and kind of go back to. So it's clear that somehow ground states must be very special. No? They don't suffer from this. They don't care about all these kind of intricacies that are possible for general random states. So ground states are very special. So what can we say about them? What kind of properties can we deduce, or what kind of simple statements can we make to kind of indeed give us some idea of how these states have to look like. Okay, and the key is actually two things. Okay, so we are talking about, so there's two things that are crucial to trying to understand ground states. On the one hand, you have locality, but on the second hand, you have symmetries. Okay, and by symmetries, actually the only one that I need now will be translation invariance. Okay, so typically I have a lattice system. This is translation invariant, and it's local. Okay, so that means that your Hamiltonian is the sum of local terms. Okay, let's assume that I'm only at I and j are nearest neighbors. And we are trying to find a state that has minimal energy. So what does that mean? Okay, so we have our kind of big lattice, all these points in our lattice. Okay, this is like my lattice. And this Hamiltonian only is dependent on, somehow this Hamiltonian acts on these two, on these two. But that means that your energy is obviously only dependent on your marginals. Okay, so to know what the energy is, let's assume that your system is translation invariant and also kind of rotation invariant. And somehow your energy of a certain state psi will be nothing more than n with n the number of terms in your Hamiltonian times the trace of somehow your local reduced density matrix acting on ij, h, ij. Okay, so let's just think about qubits. Okay, this is a lattice of all spin 1/2 systems, but at the end the energy of a state that is translation invariant is nothing more than n, with n the number of terms, times somehow your local expectation value. So yeah, maybe I have to be kind of a bit careful. Somehow, if you have Hamiltonian with translational symmetry, then actually there's guaranteed to be a ground state subspace that has the same symmetry. It does not necessarily kind of mean that there is a ground state with the same symmetry, but at least there's a ground state subspace that has the same symmetry. Okay, that's just a trivial kind of property from linear algebra. That if you have a matrix, then somehow the extremal eigenvectors have somehow the symmetry properties of the extremal subspaces of your eigenvectors, of your eigenvalues have the same kind of symmetries as your Hamiltonian. That's actually easy to prove. So what this means is that actually finding ground states amounts to identifying reduced density matrices, but extremal reduced density matrices. Reduced density matrices that have as large of an expectation value or as small an expectation value as possible for trace rho times h. Okay, because you want to minimize the energy. The energy is only dependent on the marginal, on the two kind of qubits. Okay, so you have so that means that indeed kind of a quantum state, the ground state, has like two properties. It must be kind of translation invariant, but on the other hand, it must have extremal local properties. So it must be like as close as a product state as possible, because somehow that's the only way by which you can kind of get somehow this expectation value as large as possible, but or as small as possible. Well, I was confused with small and large, but anyway. So you wanted they wanted this to be as pure as possible, because that will kind of minimize that expectation value. But on the other hand, it must have the right symmetry. Okay, and that means that that's exactly kind of the problem about monogamy of entanglement. Okay, so that's really where entanglement comes into play. Okay, so we have monogamy of entanglement. I think actually the first one to phrase or to coin that term was Barbara. But so what you have is that. Oh, well, okay, then it's Charlie Bennett. Well, you always correct me. It was the same thing with Mott. Although, about Mott, I looked it up, and the Nobel Prize winning work that he did after he was 60. But anyway. But he was certainly a physicist, and the other thing is true, he didn't start doing physics before, but I was partly right. Okay, so you have your kind of system. And let's assume that your Hamiltonian, a typical Hamiltonian that we have, is the one that I wrote down the first day, is the Heisenberg Hamiltonian. So xi, xj plus yi, yj plus... Let me actually put some kind of a parameter here, because we will need this later. J. Okay, so what is this kind of local Hamiltonian? Kind of write this down. I'm talking about qubits now. It's like it's a 4x4 matrix. So it's I will just only put somehow the non-zero elements. This is a 2, this is a 2, this is a minus delta, and this is a delta, and all the rest are zeros. Okay, so what is the ground state of that Hamiltonian? Okay, assume that delta is actually in the order of 1. Then it's very clear that somehow the ground state will be the singlet, no? Because somehow this is a 2 by 2 matrix. This is the simplest 2 by 2 matrix that you can imagine. You can certainly diagonalize it, and we'll see that the ground state of that Hamiltonian is always somehow the state 0, 1, minus 1, 0, 1 over square root of 2. That's an eigenstate of, independent actually of what this delta is. So what you see is that indeed you want to kind of locally, you want to have minimal energy locally, then you want to be as close to the singlet as possible. Okay, that means that these two sides here, they want to be in a singlet, okay, because that will minimize the energy. But of course it's translation invariant. These two kind of sides, they also want to be in a singlet. These two want to be in a singlet. They all want to be in a singlet. And we know that if somehow a qubit is maximally entangled with one next to it, then it cannot be entangled with the other one. Okay, so there will be some kind of a competition. Right? There will be a competition between how much entanglement can I share here, and the whole kind of build-up of long-range correlations and whatever you have in condensed matter physics is actually exactly by trying to play this game. How can I maximize my local? How can I get somehow as pure as possible? How can I minimize somehow this expectation value in such a way that I'm still kind of translation invariant? Okay, and that's all the kind of long-range physics or criticality and all this kind of things comes from this kind of game that nature is playing. And it's actually interesting to look at this Hamiltonian. So let's look as an example at this Hamiltonian. So there's this one parameter here. This is the anisotropy, it's called. So it happens that this Hamiltonian has lots of extra symmetries. Okay, so namely you can do an arbitrary rotation in XY plane and so further and so further. And that actually implies that the ground state, if you kind of the ground state inherits all this kind of property, that happens that this reduced density matrix of the ground state, this one, is actually guaranteed to be of the form something like 1 over 4 times the identity plus x times x tensor x plus y tensor y. So it looks very much similar to the times z tensor z. Okay, so that means that the reduced density matrices of the ground state are guaranteed to be parameterized by just 2 parameters. Okay, so let's see, you have 2 parameters, and let's kind of plot the region of. So let's try to kind of get some insight into how what will be the values of x and z for which this expectation value will be minimized. Okay, so these are just the Pauli matrices. So there's some very simple conditions. Of course, this rho has to be positive. Okay, obviously, because otherwise it cannot be a density matrix, and this actually implies that 0 is, let's see, smaller than 1 plus z is smaller or equal to 1. This is one condition, and the other condition is that 2 times the absolute value of x is smaller than 1 minus z. Okay, these are just trivial conditions, and they follow from the positivity of rho. Okay, so let's plot what these conditions do. So these are the kind of axes. Let's put the z-axis here and the x-axis there. I also don't know why I kind of did it, but this is what I did like 10 years ago, and I don't know why z is there and x there, but and you plot somehow these conditions. That means that all possible reduced density matrices must lie, to be careful, somehow in that kind of triangle. But maybe I should kind of shift this thing a little bit. No. Somehow this thing should be in the middle. Is that the middle? Okay, so that means that, so this is my kind of allowed parameters for a reduced density matrix. Namely, what are my allowed parameters of x and z for any reduced density matrix, ignoring for the moment translation invariance. Okay, so what does the singlet kind of correspond to? That ground state is exactly this point. Okay, it has kind of expectation value -1. So this is kind of this x is -1 and the z is -1. And therefore, somehow, for the Heisenberg Hamiltonian, the reduced density matrix should be such that it's as close as possible to this thing. Anyway, so this is the reduced density matrix. This is the Hamiltonian. So the energy for a given somehow parameters x and z can be easily worked out, and it's 2 times x plus z times this anisotropy, z times delta. Okay, z times delta. That's the energy for a state that has parameters x and z. So this is for a wave function with parameterized with this x and this z. So what this means is that if you want to minimize this energy, so this defines kind of planes. No? So these are all kind of this kind of equations. They are just kind of hyperplanes in my kind of convex picture here. Okay, and we know that in one dimension for this Heisenberg Hamiltonian, for example, when delta is equal to 1, we know that the ground state energy of that thing is something like minus 0.88. Okay, so we know that if we kind of draw this curve, okay, minus 0.88, that would kind of lie somewhere here, and I would kind of drive, so delta is equal to 1, so this would kind of have to be proportional to this line. Well, maybe I need a different color. So this would be kind of hyperplane. This should be blue. So I know that all physical states, therefore, must lie above that line. Okay, because I cannot have a state with energy less than minus 0.88. Okay, so all physical states must lie above this line. Okay, actually, just by symmetry, you can do the same thing here and so further. And this is for the one-dimensional case. Okay, I'm still. So it happens that you can kind of draw this. We know you can solve this whole model, this Hamiltonian in one dimension by beta ansatz. And you start doing this, and you draw kind of all these hyperplanes corresponding to the energies of x and z, and what you get is kind of a very nice kind of curve. You get something like this. Okay, and then, well, this should be completely symmetric. I'm not so sure whether I may manage. Okay, so you see that actually all physical states lie in that kind of droplet. Okay, so that's the possible reduced density matrices of translation invariant states have reduced density matrices that lie within this droplet. And the extreme points of that kind of droplet correspond one-to-one correspondence with ground states. Okay, there's only one state that has a marginal here. Namely, this will be the ground state of a Hamiltonian that would kind of has exactly this hyperplane. Okay, so the question is, how far can you push that hyperplane such that it just touches your kind of thing? So all these kind of points here are ground states. Okay, so it's kind of an interesting picture that you get. So now you can start doing the same thing in 2 dimensions. Okay, so there you can do numerics. You kind of draw this picture in 2 dimensions. And what happens is that actually you get something like this. Something like this. And something like this. It's the same Hamiltonian, translation invariant, and you say, what are the possible reduced density matrices? And what you see is that actually this thing is kind of shrinking. You can do it in 3 dimensions, you can do it 4 dimensions, and so further. And what you see is that actually this will converge to this thing. So what is this kind of diamond? This diamond in the middle. Well, actually, this is much. I draw it. This red curve is much closer to this than this. Okay, so this I'm kind of the size are not okay. So this, but what is this diamond in the middle? This is exactly kind of the states that are separable. Okay, so the states that do not have any local entanglement. These are these kind of states. And indeed, somehow, this is exactly kind of the reduced density matrix that you would get if you would work in high dimensions. Okay, instead of working 2 dimensions, 3 dimensions, 4 dimensions, you see this kind of droplet shrinks and shrinks until somehow it becomes this kind of diamond. And that's exactly kind of how mean field theory becomes exact in high dimensions. It's because somehow the possible reduced, because you have kind of a high dimensional object, and I want to have singlets between all my neighbors. But because I have to share that singlet with so many people, at the end I don't have any entanglement with anybody. Okay? And therefore somehow the only kind of solution that is compatible with this is that I don't have any entanglement at all. And that's why somehow mean field theory basically becomes exact in high dimensions. Okay, and it happens but somehow maybe I should kind of redraw this. This is actually pretty amazing. If you compare 1 to 2 dimensions, this already kind of, this 2 dimensions lies here. Okay, so this 1 dimension is very far out, and 3 dimensions is already much closer. And that's why somehow somehow, if you're interested in strongly correlated systems that have entanglement and things like that, the lower the dimension, the more entanglement there is actually. Okay, so it's exactly due to this monogamy of entanglement.
Have no entanglement. I mean,
yes.
The active grants will have some higher order entanglement, like multi-particle entanglement.
Well, if you go to if you go to kind of infinite dimensions, no, then somehow. There cannot be an entanglement because it must be all the kind of reduced density matrix would be separable, and then there's a product state that would kind of give rise to the same energy.
Could you say once again how you got that minus 0.88? Are you picking from
Oh yeah, well, this is just because I know that there's some kind of very advanced, you can solve this with beta-ansatz, and you can determine the ground state energy. So you know that basically this minus, so this is for delta is equal to 1, so you know that this is a lower bound for any x and z that is allowed. That's why we get all these hyperplanes. So the way you build up this droplet is by kind of putting all these kind of constraints. And you know that it has to lie inside, and you have kind of a continuum of kind of hyperplanes, and that's how you arrive at this picture. Actually, this picture is pretty interesting. So like in this two-dimensional case, so suddenly there's some kind of phase here. It's not curved at all. Okay, and this was kind of, I was kind of surprised to see this. Actually, what this means is that there's a first-order phase transition going on there. Okay, because you have to see, if you have a phase, and you have kind of a hyperplane, you kind of move this, you kind of turn this hyperplane, and suddenly, if you're kind of in a hyperplane here, and you turn a little bit your hyperplane, that means you change the parameter in your Hamiltonian a tiny bit, you will jump from that state to that state. That's exactly a first-order phase transition. So just by looking at somehow pictures like this, you can already see kind of lots of things about the phase diagram or phase transitions that are going on in these systems. Exactly. Okay, let's say the, how do you call this, the slope is exactly delta.
So you say that these pictures also work for the excited state?
No, I didn't say that. Why did I say, when did I say this?
Well, I mean,
No, I didn't say that. So excited states, of course, are kind of lying kind of inside, no? Because if the ground state is unique, then there's only one point here. And somehow, this is about energy densities. So basically, the excited states are also lying there, because excited states have the same energy density as the ground state. But if you kind of would do the scaling as a function of n, somehow you would...
Your friends say that they're not allowed to have entanglement.
But excited states don't have like... Excited states typically have a momentum and all this kind of thing. They don't have a translation invariance. So it's a bit... I'm just talking about ground states for the moment. I wrote a paper on that, but I don't know. But I just heard from John that apparently Kitaev had already drawn pictures like that in his bedroom, maybe, I don't know where.
It's on the whiteboard in our common room.
Well, that's what John just told. So I don't know. You can find it in the paper. Okay, the title of the paper has nothing to do with this. The title of the paper is "Matrix Product States Represent Ground States Faithfully," and what I wanted to argue in that paper. Is that indeed matrix product states are kind of good representations of any ground state in one dimension. And the reason is that if you kind of look at the reduced density matrices that you can create, so matrix product states will kind of be a family of variational states. And you can just plot the marginals of your kind of matrix product states. Okay, you can easily calculate marginals, kind of these reduced density matrices, and you plot them. And what you see is that somehow for bond dimension 1, well, you get just this mean field thing. For bond dimension 2, you're already extremely close actually to the exact kind of, the first kind of approximation, a very trivial kind of set of variational classes, the reduced density matrices already lie very, very close to somehow the exact convex set. Okay, and apparently the distance between the convex set of the variational class, so if you have a variational class, obviously the marginals must lie within the kind of marginals allowed for any possible state. And somehow the convergence of that kind of, the marginal of matrix product states is extremely fast as a function of the number of parameters. And that's basically why matrix product states kind of represent ground states so well, okay? Because the local properties can be extremely well represented, and that's the only thing that drives systems. So the only thing that matters for a ground state is to have a reduced density matrix that is as close to that thing possible. That's the only thing that determines a ground state. All the rest, like long-range correlations, all these kind of things are just a consequence of trying to do this.
There's no difference in the gapless and gap states here?
Well, if you look at the matrix product state, so there's only one gap thing here, okay? That's exactly here. This is the Heisenberg point. You see that actually in that case, the convergence is slower. So you see that indeed somehow it takes longer to touch your convex. And there's indeed somehow not, so here this is exactly the Heisenberg point. That point somehow is non-analytic, so there's some kind of non-analytic behavior there. Okay, so I still have, so how much time do I have left, John? 15 minutes? Okay, good. Okay, so let's keep this kind of two properties here that we need, and let's try to kind of build states that satisfy this, okay, that somehow have both of these properties built in. Okay, so just try to to imagine how can we kind of build up states, how can we kind of construct quantum many body states that have these kind of properties by construction. Okay, so let's first try somehow translation invariance, okay, because that's certainly the hardest one. So let's try to write down a non-trivial state that is translation invariant. Okay, so what I would do is just take some kind of a dimer state. I would take some singlets, okay, and just continue doing this. Okay, this would be a singlet, a singlet, a singlet. Okay, this is not entirely okay. It's only translation invariant if you kind of shift it by two sides, but it's still kind of okay. And so obviously somehow if you have a Hamiltonian, it will have a very strong will minimize the energy here, but it would do very, very bad there. But let's now kind of try to kind of think in terms of high energy physicists and say actually these degrees of freedom that I have here, they're not my physical degrees of freedom. Okay, there are some kind of underlying quarks or whatever. Okay, so they are just building blocks of some physical degree of freedom. And let's say that actually my physical degrees of freedom are built up by two of these virtual degrees of freedom that live in a much larger space, but I don't have access to it. Okay, so there's some kind of degrees of freedom here, just like if you kind of observe a proton, you don't have to care about somehow the quarks typically. Okay, so these are the quarks, and my physical system is actually something that lives that lives in a subspace of these kind of virtual systems. Okay, so what that means is that I will kind of just put some kind of a circle here, and this circle will be nothing more than a matrix. Okay, so this will be a matrix. So if this is this state will be something like sum I is equal to 1 to d I. Okay, this is a maximally entangled state between these kind of d-level systems. So these are d-level systems, and this kind of thing would be a map. It's nothing more than a matrix that maps a d-squared dimensional Hilbert space to a d-dimensional Hilbert space. So it's a matrix. Okay, it's a matrix. It's kind of a rectangular matrix, something like this, and it has d-squared kind of rows and small d columns. The small d, in the case of qubits, would be 2, while this big d, this large d, is just some parameter that you choose. Okay, so that means, so obviously that state is completely translation invariant by construction. Okay, because you just put these kind of things there everywhere from minus infinity to plus infinity. It certainly has the symmetry, but you also kind of feel that it will have kind of very kind of strong local correlations. Okay, because somehow if I calculate a reduced density matrix between these two particles, somehow there's lots and lots of kind of entanglement here. Okay, so they will be able to talk to each other, and the effect of everything outside will kind of typically be damped. Okay, so somehow what happens here will not affect this. Okay, there's some kind of, because it's far away from it. Okay, this will not care. So you see that indeed somehow these states, they seem to kind of capture both of these properties. They will be able to kind of build up very strong local correlations, and nevertheless they are translation invariant. And indeed somehow these states are called kind of matrix product states. And I will spend lots of time now kind of trying to kind of study the properties of these states. Yes?
Just to make sure I understand what exactly they are. So you start from the singlets?
Or some higher dimensional kind of singlets, yes.
And then you map from d squared to d, but what's the mapping?
Just, these will be the parameters. So this is a matrix. We call it AI, we will call them. And these are parameters. These are free parameters. And it will happen, so, and indeed this will become a variational class. And these matrix will exactly be somehow the variational parameters. And what I said to you before, that somehow when you looked at this convex set, for this large d equal to 2, I was already able to kind of get something very, very close to the exact convex set. It exactly means that somehow this d, so this is a 4×2 matrix in that kind. So this would be a 4×2 matrix, so it only has like 8 parameters. With these 8 parameters, I would already be able to kind of reproduce basically the essential features of any kind of ground state of that kind of Hamiltonian model that I showed you there. Okay, but the whole thing is so what will happen is that actually any ground state of a gapped local Hamiltonian in one dimension will kind of you will be able to represent it very accurately using somehow states of that form. Okay, maybe this kind of bond dimension will have to grow a little bit. Instead of 2, it has to be like 100. But it doesn't matter. Somehow in practice we can extremely we can deal with this, and we will be able to do the variational calculations very well. So what a crucial property of these states is that indeed you can calculate things with it. You can easily kind of calculate correlation functions, you can easily do the variational calculation, you can minimize the energy as a function of these parameters, you can all do this kind of things, and I will kind of try to sketch a little bit how what the properties of these states. But of course, this kind of construction is not restricted to one dimension. You can also immediately do it in 2 dimensions. Okay, so the only thing you do is kind of add some. Well, maybe I should. So you add some. Start with your kind of quarks, and you just put them there. And now your map is somehow from d to the 4 to d. Okay, so you get much more. You get more variational parameters. But again, somehow these states have exactly the same properties. They have kind of the locality, and they have a translation invariance. And also there in 2 dimensions, it happens that this captures really very well the physics of any kind of ground state of a local Hamiltonian. Okay, so
Does this define a linear space? Does it not?
no, it's a very nonlinear map, no, because you have a map here, but you have the same map there. You have the same map everywhere, so it's a multilinear. No, the bond dimension has to be the sum of the 2 bond dimensions. You can easily see that actually you can, by taking the sum of 2 states, then you can, this is again nothing more than a matrix product state, where the bond dimension is the sum of the 2 bond dimensions. So indeed it doesn't, you can, but that's, I will kind of explain this well, but I probably have not much time, but that somehow the whole idea is well, maybe let me try to see how I can sketch it. So actually, yeah. Well, so one property that these states have by construction is that they have an area. They obey an area law. Okay, so that's very easy to see. So you have this matrix or in 2 dimension. It doesn't. It both helps in 1 dimension and 2 dimension. Okay, so let's kind of take a block of spins and calculate the reduced density matrix for these things. Okay, so what we will have to do is trace out basically everything from the left. We have to trace everything that comes from the right. You see that actually the only connection between inside and outside is via this bond. And therefore you will be able to prove directly that the rank of this density matrix is bounded by the product of this bond dimension and this bond dimension. Okay, so in that particular case, the rank of any reduced density matrix, independent of how many sides you have, is actually equal or bounded by d squared. Okay, so this automatically has an area law. Okay, so it's the amount of entanglement in your kind of system is of course bounded by somehow the log of the rank of your kind of thing, and you see that indeed somehow that means that these things for a finite d obey an area law. But we also know that that ground states of 1-dimensional gapped quantum systems actually obey an area law. Okay, so that's compatible. I wanted to sketch briefly somehow how you prove that quantum many body systems in 1 dimension of gapped kind of local Hamiltonians kind of obey an area law. This is again using this kind of Lieb-Robinson bound techniques, this Quasiadiabatic evolution. You need all these kind of things, and then you can actually prove that any kind of ground state has these properties. So that is actually pretty exciting. So what it means is that that ground states of local Hamiltonians in 1D can be parameterized efficiently, okay, using some kind of a bond dimension, and somehow you have to be a little bit careful in how this D grows as a function of the entanglement, but somehow if you have an area law, you can prove that actually the overlap of the exact ground states with one of these kind of matrix product states can be made arbitrarily small, and the scaling of D with the error is actually polynomial. It's not exponential. So what you have is really a breaking down of this exponential wall by which you would need exponentially many parameters to describe a many body system. So here somehow with a polynomial number of parameters, you can describe a ground state to arbitrary precision. Okay? The complexity of describing it as a function of the precision only grows polynomially with the system size. Well, yeah, I wanted to say much more, but I really don't see how I kind of can fit this in. But anyway, so what is the bigger picture? Okay, why does this two-dimensional thing obey an area law? It's exactly the same reason. No? You kind of take any kind of region, and the rank of this reduced density matrix will kind of be bounded by the product of all these kind of bonds, all these maximally entangled states that you cut. But of course, the number of singlets that you have here is bounded by somehow the surface, and therefore you automatically have an area law. Okay, so why is it? So I will also spend some time later about these kind of systems in 2 dimensions because they are particularly interesting to elucidate somehow these properties of topological order. It happens that all these toy models that people have been playing around with, like the toric code state, the Levin-Wen models, the quantum doubles, all these kind of models, they have an extremely concise description in terms of these kind of matrix of these PEPs. So we call actually these 2-dimensional generalizations, we call it projected entangled pair states, okay? Because you have kind of entangled pair states and you project them down by this kind of matrices. Okay, and it happens that this captures very, very well somehow the properties of topological order. And the reason why they are so exciting for describing topological order is that you will have topological order if and only if these kind of tensors, okay, because you see this is a tensor that maps 4 indices to 1, will need to have some specific symmetries. Okay, you will be able to kind of see that this state has topological order by just looking at the symmetries of that kind of tensor. And if these symmetries are not present, you cannot have topological order. If they are present, then typically they will be present. Okay, modulo some kind of complications, but somehow there's a way of understanding topological order kind of quantum spin systems in this language.
To understand the methodology, you have these tensors. How do you know whether they follow the symmetries or not? You need to calculate them?
Yeah, so for a given model, like give the toric code, well, I can give you this tensor. And then you will study the properties of that tensor, and you will see that there's some kind of hidden symmetries there.
But how do you calculate that tensor?
Oh, for these models like the toric code or the Levin-Wen models, there's an easy way of finding actually what these tensors are.
So you basically read them off the Hamiltonian?
Yes, because all these kind of cases are very simple because somehow these are ground states of local commuting Hamiltonians. Okay, so all the terms in your Hamiltonian commute with each other, and therefore you're in the ground state of every individual term. And then basically, why can you immediately see that the ground state of a Hamiltonian that is frustration-free and all the terms commute cannot be written as X? You just put projectors. I just project here in the ground state of that part, and then I project there, and these things commute. And I keep on projecting. And you see that there's indeed a local description in terms, and then there's a kind of a bit of work to kind of turn something like a projection of these 4 into kind of a description in terms of these tensors, but it's actually pretty straightforward to do these things.
Okay, so these kind of states you can calculate also ground states.
Yeah, but of course the big thing is that you can deform them now. Okay, so you can really kind of add a correlation length to them because all these states that people look at, they are all kind of, well, they are fixed points of renormalization groups and they have 0 correlation length and all these kind of things. So now we can start deforming this by just changing the parameters in these tensors. You see that there's a kind of a string tension that you can play all these games by just looking at these states. Okay, so anyway, so what is the most important message is actually that we have a parameterization of this kind of manifold of all ground states of local Hamiltonians, at least in 1D. And in 2D, as we have seen, we'll have kind of many of these equivalence classes. And all these different equivalence classes typically will kind of correspond to different types of topological order. Okay, so what is the crucial idea actually from the theoretical point of view? So why is this kind of way of looking at quantum many-body states so exciting? So let me just read a quote of Feynman about something that he wanted to do. Okay, so what he said is the following, and I think it fits very well with also the other talks. So it's really quite insane actually. We are trying to find the energy by taking the expectation value of an operator which is located here. Okay, so you have a kind of a local operator, you want to minimize whatever, you want to calculate the expectation value of a local operator of some kind of a ground state. Okay, and present ourselves with a functional which is dependent on everything all over the map. That's something wrong. Maybe there is a way of surrounding the object or the region where we want to calculate things by a surface and describe what things are coming in across the surface. It tells us everything that's going on inside or outside. I'm talking about a new kind of idea, but that's the kind of stuff we shouldn't talk about at the talk. That's the stuff we should actually do. That's literally kind of what he said when he was thinking about variational methods for simulating quantum field theories. And this is exactly what is going on here. Okay, so this is exactly, if you kind of think a little bit about this is exactly why somehow, this is exactly what the essence is of this method. So what you have is this kind of matrix product state. You want to calculate an expectation value here. Okay, so that means that you have to, well, let me represent actually this kind of thing, this tensor. I can also kind of look at it as something like this. and every time I have this is kind of this tensor. Okay, so I have here my bond dimension, this is dimension D, big D, this is dimension small d, and I have this kind of matrix product state. And I want to calculate an expectation value, let's say here, an operator. Okay, and you want to calculate the expectation value, then of course you have to surround it. Or let's say we acted on more sides. We want to calculate expectation values here. Okay, so then we have to kind of take the complex conjugate of this thing. Okay, so you see this goes to infinity. So where is the information that you need from the outside to calculate the expectation values of that kind of local operator? It's all in this kind of two indices. Okay, that means that actually you come from infinity and you can just contract this whole tensor network. And the only thing you will kind of remain with is something like this. And this contains all the information about what happens outside for calculating this expectation value. You do the same thing from the right. You come from infinity and at the end you kind of contract all this thing, and all the information at the end will be in some kind of an object that lives here. Okay, and that's what we kind of call some kind of a holographic kind of thing, no? Because all the information, it's possible to kind of store all the information of the outside in some kind of in the boundary of this kind of thing. In 2 dimensions, it's more interesting. No? In 2 dimensions, somehow all the information will be in some kind of a theory that lives on this border. Okay, but this border somehow has these virtual indices. Okay, so in this 2-dimensional case, it means that actually everything that goes outside of that region, you will be able to describe by a theory that lives in this space of these quarks. Okay, so these virtual degrees of freedom are actually playing a very physical role because they kind of parameterize exactly what is going on outside. So they're doing exactly what kind of Feynman was envisioning. And I think I have to stop. Thanks.
I want to say that this, what you call the Quasiadiabatic Evolution, was first introduced by Toshio Kato in 1950-something, when he proved the adiabatic theorem. He gave the first rigorous proof of the adiabatic theorem, and then this type of evolution was used, in fact, in all rigorous work on the adiabatic theorem. I also wanted to say that I really don't like the name quasi-adiabatic, because if anything, it is super hyper adiabatic. It's not quasi, it's much
Oh,
better
I can.
than quasi.
Yeah.
But I should say that I think the beautiful contribution of Hastings to this story was the recognition that the generator could still be written as a local object.
Oh, yeah, of course. That's the whole clue. That's the clue. That's the point.
Thing, but the generator was written.
But I also think so. I'm not so sure that in the 50s these results from Fourier analysis were already known.
Oh, of course, this was
Yeah?
known forever.
Really, that you have compact support and all this. Well, no.
This is just Fourier analysis, this harmonic analysis. People are
No, but these are these kind of so-called bump functions, and this is actually pretty well.
Barnes knew this.
Well. No, but so the genius of Hastings is to recognize that this can be used to prove things, like to use this to prove Goldstones Theorem. It's amazing, no? You can do it in 2 lines, but you have to see it, okay? And that's.
He's great. Hastings is great.
Yes.
It follows straightforwardly that you have an area law in any dimension, no?
No, wait. I never said that like in higher dimensions, every ground state can be written like this. Okay, so indeed, this is a good candidate.
No, for major product states, it follows directly that they follow an area law.
Well, you have to do it the other way. You have to prove that every ground state obeys an area law, and therefore somehow you can prove that they can be written as a matrix product state. That's actually the way you prove it. So you first have to prove that there's very few entanglement, and because there's so few entanglement, somehow this is a good description. So indeed, I think that's actually, if there's one message that is important in this whole thing, is that ground states have very, very few entanglement. Okay, exponentially less than you would kind of usually think. That's the whole point of the area law, and that's why somehow we can actually work. We can actually deal with ground states. We can describe them. We kind of use them. It's just because there's so few entanglement. Even if you have a critical system, actually, if you have a critical system, the amount of entanglement is actually not. So for a critical system, this D actually has to grow with the system size and things like that. But even then, the entanglement entropy is only growing like the log of the size of the block. And that's still exponentially less than you would have for a random state. So even critical systems can actually be extremely well described by such matrix product states.